live in an age of flying robots, where soldiers can wage war without the risk of dying in return.
We are seeing a large-scale drone operation in about 6 countries around the world that are conducting assassinations on a daily basis.
The United States now trains more drone pilots than it trains normal aircraft fighter jet pilots. We see that the estimates are that by 2025, maybe 2030, 100% of the entire American Air Force fleet will be unmanned.
The rise of military drones is crossing over into civilian airspace.
So people, they hear the word drones, they hear about unmanned aircraft, and they instantly associate with Afghanistan, Iraq and so forth. On the other hand, we've got a lot of great potential for social and beneficial application.
But deploying the new technologies brings a host of legal and regulatory issues.
The ethical issue that is on the horizon is one of surveillance, and whether certain institutions will be allowed to fly drones in the air over neighborhoods, survey populations. Who's going to have that power? Who is not going to have that power?
And is there a safe way for unmanned aircraft to share our skies? Scientists in Queensland are figuring out how.
Really what we're looking at is robotics meets aviation. So the question is, what are the safety technologies that we need on the aircraft so that they can autonomously detect and avoid other aircraft, and if there's an engine failure or some other emergency, they can land themselves safely.
The machines are coming. We have to adapt to a new kind of civic ecology.
There's plenty of optimism about the use of flying robots for civilian purposes. Everything from search and rescue to even pizza delivery. But when it comes to where the technology is really at, is there a gap between expectation and reality?
This lab at the University of Pennsylvania is building light, agile, low-powered UAVs that are completely autonomous. Tiny yet powerful computer processors enable them to figure out how to get from one point to another. They sense where other machines are and fly in formation. They maintain their position and navigate obstacles. Unlike these indoor acrobats, however, unmanned aircraft in the real world remain under remote control by a team of people on the ground. They also have to be large enough to carry a payload and enough batteries or fuel to keep them flying. This Global Hawk drone has the wingspan of a 737.
The motivation is not so much necessarily to replace manned with unmanned, it's really to complement that.
For example, in a natural disaster, UAVs could search for survivors, freeing up conventional aircraft to undertake rescue operations. Drones carrying cameras were used to assess the damage to nuclear reactors at Fukushima.
One of the things that we look at is dirty, dull and dangerous. And so things that are too dirty, dull or dangerous for manned operations, we then can supplement or augment with unmanned aircraft, get a much greater utilisation of the facilities that we have.
Before flying robots are allowed to inhabit our airspace, they'll have to be able to prove they can do what piloted aircraft already do. Follow the traffic rules, avoid collisions and land safely in an emergency.
Research to enable that starts here with an experienced pilot and his trusty Cessna.
In real aircraft, there's a pilot. The pilot can control the aircraft and land it, even without an engine. In a UAV, there is no pilot, so we need to use computers and mimic human behavior and teach a computer that it does the same as a human pilot and lands the UAV platform safely.
Dirk, is this what it takes to recreate your brain?
Basically, yes.
The onboard computers record the pilot's every move, as well as altitude, direction, and how the plane responds. The processors convert Dirk's intuition and training into hard data. They gather information about the physics of the aircraft when Dirk deliberately shuts off the engine to recreate an emergency landing.
there's no thrust from the propeller. So that means you will slow down, and if you don't maintain the best glide speed, then the aircraft will just stall.
Just as pilots need to know how to find a landing site, so too do UAVs. And that means they need some autonomy based on data from the real world. Luis Mejias takes the data from the plane to develop algorithms, that is, writing sets of rules in computer code to enable an unmanned system to solve problems for itself.
I try to replicate human capabilities and try to transfer that to a machine by developing computer programs that can see, think, react.
The test flights of his automated landing system happen safely inside his computer simulator. Today, the engine suddenly fails.
Vertical speed is approximately 600 feet per minute. Descending rate, 600 feet per minute.
So it's dropping out of the sky?
Yes. This point is the initial position of the aircraft where the failure occurred. So at that point, the system did three functions. Identified a landing site on the ground. Second, generated a trajectory to that landing site. And the third, assessing the situation to decide which of those landing sites was the best. So the red line is the actual trajectory of the aircraft, and it's trying to follow the green dots, which are actually waypoints that are being generated by the algorithm.
So even though the trajectory didn't land right on the site it identified, is that close enough?
It was close enough. The difference was just a few meters.
And it lands safely?
And it landed safely. It didn't crash.
So I'm just shortening the screen.
The next step in these experiments is to scale down the computer hardware and load these algorithms onto a UAV. However, judging from the state of the aircraft on the workshop bench, there's still some work to go before the first test flight. Elsewhere in the world, similar algorithmic software is used in UAVs designed to fly out of this world. This is NASA's first free flight of a test rocket for delivering humans or robots to the surface of the Moon, Mars, or even asteroids. Although the flight lasts just over a minute, it flies autonomously 50 metres high, tracks sideways to find another landing site, then heads straight down. A small hop for NASA, a giant leap for UAVs.
We like to think that life under drones is something that happens to other people in other countries. But keep in mind, that future for our cities may be coming sooner than we realise.
Certainly in my lifetime, they're going to be part of everyday life. I live in inner city Brisbane. I have the traffic helicopters hovering overhead, and I could quite see the day where there might be a mixture of manned and unmanned vehicles monitoring traffic.
If drone technology can meet safety conditions set by regulators, they'll be permitted to fly above populated areas. They're perfect for surveillance, and that raises concerns about privacy. The US military has surveillance drones that carry a powerful camera system called Argus-IS. From a height of more than 6 kilometres, its video eye can see objects as small as 15 centimetres.
And the drone is hovering over Baghdad 24 hours a day, collecting terabytes of visual information and tracking the whereabouts of essentially all the inhabitants of Baghdad. It's not inconceivable that the Argus-IS project will be applied to every major city in the United States, or perhaps someday in Australia as well.
While that may sound far-fetched, the US Federal Aviation Administration has recently authorised the first military drones to be used commercially for domestic aerial surveillance.
Now we've seen CCTV cameras popping up left, right and center in all cities around the globe, and there seems to be a larger demand to get them year in, year out. The drone is just another form of surveillance.
And that's the question for us to consider. Is that future of robot surveillance one we're comfortable with?